In the frozen darkness beyond the orbit of Jupiter, far past the warmth of the Sun, a quiet rebellion is taking place. There, circling the ringed giant Saturn, a small, battered moon moves in defiance of expectation, while almost everything in the solar system flows in the same graceful direction. Planets orbiting the Sun, moons orbiting their planets, rings spinning in coordinated harmony, this object travels the other way. Backwards, against the cosmic current. Its name is Phoebe. Phoebe does not glide neatly alongside Saturn's major moons. It does not follow the orderly choreography laid down when the solar system formed 4.5 billion years ago. Instead, it plunges around Saturn in a steep, tilted path, moving opposite the planet's rotation. Retrograde, rebellious, alien. For over a century, astronomers have stared at Phoebe and asked the same unsettling question: how did this moon end up going the wrong way? Was it born around Saturn and somehow thrown into reverse? Was it captured from deep space? Could it be a relic from the distant, icy frontier beyond Neptune, stolen long ago by Saturn's gravity? And if so, what does that mean for the violent history of our solar system? This is not just the story of a moon with an unusual orbit. It is a story about chaos in the early solar system, about gravitational battles between giants, about wandering worlds that reshaped planetary systems, and about how a single dark, cratered object orbiting in silence can rewrite our understanding of how planets and moons are made. For decades, Phoebe was a mystery glimpsed only as a faint speck of light. Then, in 2004, a spacecraft from Earth approached it at breathtaking speed, revealing a world unlike any other moon of Saturn. Its surface, its density, its chemistry. Everything about it suggested that Phoebe did not belong. We finally know why Phoebe orbits backwards. But to understand that answer, we must go back to the beginning, before Saturn had rings, before the giant planets settled into their current positions, before the solar system became the orderly place we think we know. Because Phoebe is not just orbiting backwards, it is orbiting from another world. If you're fascinated by the strange, overlooked corners of our universe, subscribe to The Boring Universe. Like this video to help others discover it, and leave a comment telling us which part of the country you're watching from. Now, let's begin. To understand why Phoebe's backward orbit is so extraordinary, we must first understand the rule it breaks. The solar system at first glance appears chaotic. Asteroids tumble unpredictably. Comets plunge in from the darkness. Moons vary wildly in size, shape, and composition. But beneath this apparent disorder lies a powerful underlying structure. Almost everything moves the same way. The planets orbit the Sun in a counterclockwise direction when viewed from above the Sun's north pole. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune all follow this shared path. They also orbit in roughly the same flat plane, like grooves on a cosmic vinyl record. This alignment is not a coincidence. It is the fossil imprint of the solar system's birth. Around 4.6 billion years ago, our solar system began as a vast cloud of gas and dust known as the solar nebula. This cloud, likely disturbed by a nearby supernova, began to collapse under its own gravity. As it collapsed, it started to spin, and as any spinning cloud contracts, it spins faster, just as a figure skater spins faster when pulling in their arms. This rotation flattened the cloud into a disk. At the center, matter condensed into the proto-sun. In the surrounding disk, dust grains collided and stuck together, forming larger and larger bodies. Over millions of years, these grew into planetesimals, then protoplanets, and eventually the planets we know today. Because everything formed from this same rotating disk, everything inherited its direction of motion. The Sun spins in one direction. The planets orbit in that direction. Most moons orbit their planets in that direction. Even the rings of Saturn follow the same rule. This shared motion is known as prograde rotation. It is the default state of a planetary system formed from a rotating disk. It is the expectation written into the physics of gravitational collapse. And then there are the exceptions. Among Saturn's more than 140 known moons, most of the large inner ones obey the rule. Titan, Saturn's massive atmosphere-shrouded giant, orbits prograde. Enceladus, famous for its geysers of water ice, orbits prograde. The major moons move in near-circular paths, aligned closely with Saturn's equator. They behave like children born into Saturn's gravitational family. Phoebe does not. Phoebe's orbit is tilted by about 175 degrees relative to Saturn's equator. That means it moves almost perfectly opposite the direction of Saturn's rotation. Instead of following the same counterclockwise direction as most of Saturn's moons, Phoebe moves clockwise. In celestial mechanics, this is called a retrograde orbit. Retrograde motion is not just unusual. It is a sign of violence. If Phoebe had formed in the same circumplanetary disk that produced Titan and Enceladus, it would share their direction of motion. The disk itself rotated in a single direction, inherited from the solar nebula. There is no natural mechanism within a calm, rotating disk to produce a large moon moving backwards. So when astronomers first calculated Phoebe's orbit in the early 20th century, alarm bells rang quietly in the background of planetary science. Phoebe was discovered in 1899 by the American astronomer William Henry Pickering. Unlike Saturn's brighter moons, which had been known since the time of Galileo, Phoebe was faint and distant. Even in large telescopes, it appeared as little more than a dim point of light. Its orbital distance alone was startling. Phoebe circles Saturn at an average distance of nearly 13 million kilometers, far beyond the main ring system and the major inner moons. For comparison, Titan orbits at just over 1.2 million kilometers. Phoebe is more than 10 times farther out. At that distance, Saturn's gravitational grip is weaker. Objects there are more susceptible to perturbations from the Sun and other planets. Orbits are less stable over billions of years. Phoebe's path is also highly eccentric, meaning it is elongated rather than circular. Combined with its retrograde direction and extreme tilt, this painted a picture of something fundamentally different. Astronomers began classifying moons into two broad categories, regular and irregular. Regular moons are those that orbit close to their planet, in near-circular, low-inclination, prograde orbits. They are thought to have formed from disks of gas and dust surrounding young planets, much like miniature versions of the solar nebula. Irregular moons, by contrast, orbit far from their planet, often in highly inclined or retrograde paths. Their orbits are eccentric and sometimes unstable. They do not fit neatly into the formation story of the regular moons. Phoebe became the archetype of an irregular moon. But classification is not explanation. Why would Saturn have an irregular moon at all? And why would it be moving backwards? To answer that, we must consider gravity not as a gentle sculptor, but as a thief. When planets form, they do not exist in isolation. In the early solar system, countless leftover planetesimals roamed the space between worlds. The giant planets Jupiter, Saturn, Uranus, Neptune were surrounded by swarms of debris. These objects occasionally passed near the planets, sometimes close enough to be dramatically affected by their gravity. In theory, a planet can capture a passing object, but in practice, this is extraordinarily difficult. If an object approaches a planet, gravity accelerates it. As it falls toward the planet, it gains speed. Unless something removes energy from the system, the object will simply swing around the planet and escape back into space, like a slingshot maneuver used by spacecraft. For permanent capture to occur, energy must be lost. In the early solar system, there were mechanisms that could allow this. A passing object might collide with another body, losing speed. It might pass through a thick disk of gas surrounding a young planet, experiencing drag. Or it might interact gravitationally with multiple bodies in a complex three-body encounter, transferring energy elsewhere. If such a capture happened, the resulting orbit would not be neat or aligned. It would reflect the random geometry of the encounter. The captured object could orbit at a steep angle. It could move in a retrograde direction. It could have a highly eccentric path. In other words, it would look exactly like Phoebe. By the mid-20th century, many astronomers suspected that Phoebe was not born around Saturn at all. It was captured. But captured from where? At first, this question was almost impossible to answer. Phoebe was too distant and too small for detailed observations. All scientists had was its orbit and a rough estimate of its brightness. Then came the age of spacecraft exploration. When the Voyager 2 flew past Saturn in 1981, it captured the first close images of Phoebe. Even then, the moon appeared only as a small, irregular blob. But those images hinted at a dark surface, heavily cratered, more like an asteroid than a typical icy moon. The real breakthrough came decades later, with the arrival of the Cassini-Huygens mission in 2004. Before settling into orbit around Saturn, Cassini executed a daring flyby of Phoebe. It approached within about 2,000 kilometers of the moon, capturing detailed images and collecting data about its composition, mass, and structure. What Cassini found would transform our understanding of Phoebe and of the outer solar system itself. Phoebe was not just irregular in its orbit. It was foreign in its very substance. Its surface was dark, coated in carbon-rich material. Its density was higher than expected for an icy moon of Saturn, suggesting a mixture of rock and ice more typical of bodies from the outer solar system. Spectral analysis revealed the presence of water ice, carbon dioxide, complex organic compounds, and materials rarely seen on Saturn's inner moons. Phoebe looked less like a child of Saturn and more like a refugee from the distant Kuiper Belt, the vast region beyond Neptune filled with icy remnants of planetary formation. If that were true, it would mean that Saturn had captured a fragment of the outer solar system, a relic from beyond Neptune, dragged inward and forced into a backward orbit around a gas giant. But that explanation required something even more dramatic, a reshuffling of the giant planets themselves. Because for Saturn to capture an object from so far away, the architecture of the early solar system must have been far more dynamic than we once believed. Phoebe's backward orbit was not just a curiosity, it was a clue that the outer solar system was once a battlefield, a clue that Saturn did not always reside where it does today, a clue that the serene order we see now emerged from a period of profound instability. In the darkness beyond the rings of Saturn, Phoebe continues its slow, retrograde journey, carrying within it the memory of that chaos. We will follow that memory back to a time when the giant planets migrated across the solar system, scattering worlds like cosmic billiard balls, and when a small, icy body from the edge of the Sun's domain found itself captured, forever moving against the flow. Phoebe's backward orbit tells us that it does not belong to Saturn's original family of moons. Its steep inclination, its eccentric path, and its vast distance from the planet all point toward a violent origin. But identifying Phoebe as a captured object only deepens the mystery. Capture, in the realm of orbital mechanics, is not simple, it is not common, and it is not gentle. To understand why, we must examine the physics that govern motion in space. Every object moving through the solar system carries energy. When a small body approaches a massive planet like Saturn, gravity pulls it inward, accelerating it to higher speeds. As it swings past the planet, that same gravitational force can redirect its path, bending its trajectory dramatically. But unless the object loses energy during this encounter, it will not remain bound. It will escape, flung back into space along a new course. This is the fundamental obstacle to permanent capture. In a simple two-body interaction, one planet and one passing object, energy is conserved. The object may change direction, but its total energy relative to the planet remains the same. If it arrived unbound, it will depart unbound. So how do you capture something that does not want to stay? The answer lies in complexity. In the early solar system, gravity did not operate in neat, isolated pairs. It operated in crowds. Billions of years ago, the outer solar system was dense with debris. The giant planets were still forming, surrounded by thick disks of gas and countless leftover planetesimals. Massive objects were migrating. Smaller bodies were colliding. The environment was chaotic, dynamic, and crowded. In such a setting, capture becomes possible because energy can be redistributed. Imagine a small icy body traveling inward from the outer reaches of the solar system. As it approaches Saturn, it enters the planet's gravitational sphere of influence, a region known as the Hill sphere. Within this domain, Saturn's gravity dominates over that of the Sun. But the object is still moving fast, and without interference, it will simply slingshot past. Now introduce a third participant. Perhaps another moonlet is nearby. Perhaps a cloud of gas surrounds the young planet. Perhaps Saturn itself is not yet in its present orbit and is moving relative to the surrounding swarm of planetesimals. In these situations, gravitational interactions can transfer energy between bodies. If the passing object loses enough kinetic energy, through collision, gas drag, or a complex three-body interaction, it can drop into a bound orbit around the planet. The once transient visitor becomes a permanent satellite. But this process leaves scars. Captured objects do not settle into neat, circular equatorial orbits. They retain the imprint of their chaotic arrival. Their orbits are often highly inclined. They may be elongated. And critically, they may move in a retrograde direction. In fact, retrograde capture can be dynamically favored in certain scenarios. When an object approaches a planet from the opposite direction of the planet's motion around the Sun, the relative velocity between them can be reduced in the planet's frame of reference, making capture more likely under specific conditions. The mathematics of celestial mechanics reveals that retrograde orbits can be more stable at large distances within a planet's Hill sphere. This counterintuitive stability is key. Far from the planet where solar gravitational perturbations are significant, prograde orbits can become unstable more easily than retrograde ones. Retrograde satellites experience different resonant interactions with the Sun, often allowing them to survive for billions of years where comparable prograde orbits might be disrupted. Phoebe's orbit, tilted by about 175 degrees relative to Saturn's equator, places it almost perfectly in this retrograde regime. It moves nearly opposite Saturn's rotation and far beyond the regular moons. Its survival over the age of the solar system suggests that once captured, its unusual orbit became dynamically protected. But capture from where? By the late 20th century, planetary scientists began to suspect that the outer solar system had once been arranged very differently. The neat configuration we see today, Jupiter at 5.2 astronomical units, Saturn at 9.5, Uranus and Neptune farther still, might not reflect the planet's birthplaces. This idea gained traction with the development of the Nice model, named after the city in France where it was formulated. According to this model, the giant planets formed in a more compact configuration. Beyond them lay a massive disk of icy planetesimals extending outward, a primordial version of what we now call the Kuiper Belt. Over hundreds of millions of years, gravitational interactions between the planets in this disk caused the giant planets to migrate. Jupiter moved slightly inward. Saturn, Uranus, and Neptune moved outward. As they migrated, they scattered countless icy bodies. Some were ejected into interstellar space. Some were flung inward, contributing to a period known as the Late Heavy Bombardment, when impacts reshaped the inner planets, and some were captured. This era of instability would have provided ideal conditions for Saturn to snare an object from the outer solar system. If Phoebe originated in that distant disk beyond the early orbit of Neptune, it would have been composed of a mixture of rock and volatile ices, similar to modern Kuiper Belt objects. Its dark, carbon-rich surface would reflect primordial chemistry, largely unaltered since the solar system's formation. When the Cassini-Huygens mission flew past Phoebe in June 2004, it gathered precisely the data needed to test this hypothesis. Cassini measured Phoebe's mass by tracking its gravitational influence on the spacecraft's trajectory. Combining this with imaging data allowed scientists to calculate its density. The result was striking. Phoebe's density is about 1.6 grams per cubic centimeter, significantly higher than that of Saturn's inner icy moons, but consistent with a mixture of rock and ice typical of outer solar system bodies. Spectroscopic analysis revealed the presence of water ice, carbon dioxide ice, and complex organic molecules. The surface was dark, with albedo characteristics resembling those of objects in the Kuiper Belt rather than Saturn's brighter regular satellites. Cassini's high-resolution images showed a heavily cratered world, saturated with impact scars. Some craters were enormous relative to Phoebe's size, indicating a violent collisional history. The moon's irregular, somewhat lumpy shape suggested it had not undergone the same internal heating and differentiation as larger moons like Titan. Taken together, these findings painted a coherent picture. Phoebe was not born in orbit around Saturn. It formed in the cold outskirts of the solar system and was later captured. But the capture itself required a specific set of circumstances. One leading hypothesis involves three body interactions during the period of planetary migration. As Saturn moved outward, it would have encountered countless icy planetesimals. If Phoebe was once part of a binary system, a pair of objects gravitationally bound to each other, the gravitational field of Saturn could have disrupted the pair during a close encounter. One component might have been ejected, carrying away excess energy, while the other became bound to Saturn. This binary capture mechanism has been proposed to explain other irregular satellites as well. It is dynamically plausible and consistent with simulations of early solar system evolution. Another possibility involves gas drag. During the final stages of Saturn's formation, the planet was likely surrounded by an extended envelope of gas. A passing object moving through this gas would experience friction, losing energy and potentially becoming trapped in orbit. However, this mechanism requires that the gas envelope still be present at the time of encounter, placing constraints on the timing of capture. Current evidence favors a gravitational capture scenario linked to planetary migration rather than gas drag. Phoebe's composition aligns closely with outer solar system bodies, supporting an origin beyond Neptune. Its retrograde orbit, high inclination, and eccentricity match the expected signatures of captured irregular satellites. Phoebe is not alone in this category. Saturn possesses dozens of irregular moons, many also in retrograde orbits. They form families, clusters of objects with similar orbital parameters, suggesting they may be fragments of larger bodies shattered by collisions after capture. Phoebe, however, stands apart. It is larger than most irregular satellites and may represent a surviving primordial object rather than a fragment. Some scientists even consider the possibility that other small irregular moons are debris from collisions involving Phoebe itself. In 2009, astronomers discovered a vast, diffuse ring of material associated with Phoebe's orbit, now known as the Phoebe ring. This ring extends millions of kilometers and is composed of dark particles likely shed from Phoebe by micrometeoroid impacts. Some of this material spirals inward and settles onto the surface of Saturn's moon Iapetus, contributing to its striking two-toned appearance. Thus, Phoebe is not merely a captured relic. It is an active participant in Saturn's system, influencing other moons through a slow rain of dark debris. The backward orbit that once seemed like a curiosity is now understood as a signature of origin. It tells us that the solar system was not born in quiet symmetry. It was shaped by migration, scattering, and capture. The giant planets did not remain fixed. They moved, and in moving, they rearranged the architecture of the Sun's domain. Phoebe's retrograde path is the fossil trace of that upheaval. By studying its motion, composition, and history, we are reconstructing a chapter of solar system evolution that was once invisible. The calm, orderly configuration we observe today is the end result of a turbulent youth. Far beyond Saturn's bright rings and luminous inner moons, Phoebe continues its lonely, backward journey. It circles the planet every 550 days, silent and dark, a survivor of gravitational battles fought billions of years ago. And in its stubborn defiance of the solar system's dominant direction, Phoebe preserves a truth that reshapes our understanding of planetary systems everywhere. Order is not the starting point of cosmic history. It is the fragile outcome of chaos.